All right, hello mathematicians. We're looking at section 3.3 where we start to get into the rules for differentiation. Please copy down these notes into your packet. And task number 1 asks you to write down a few definitions from memory. So I would pause the video if you could. See if you can write down what does it mean for a function to be continuous, continuous on an interval, and continuous in general. Then we'll apply those ideas to differentiability. Okay, so let's see what those definitions are. Just recall, a function is continuous if three conditions hold. It's continuous at a point x equals a. If the point exists or the function is defined at that point, the limit as x approaches a exists. The limit as x approaches a of f of x exists, and you can use the limit notation there. And then third, this is the most important feature. I'll write it like this. The limit as x approaches a of f of x equals f of a. You can use that nice limit notation to make that down. Now, this is the most important condition. And you technically could give the definition of continuity just by providing this third condition. And in so doing, you're kind of saying that, well, yes, we're writing down this limit, we're saying it equals f of a, and that implies that f of a exists and is a finite number. So if you're going to remember just one of them, do this one, or you can remember the three-part definition, which is helpful to say why a function is not continuous in certain cases. Now, it's continuous on an interval if f is continuous at every point of that interval. We've seen that before. This one's tricky. It's continuous in general if f is continuous at every point of its domain. And the example we used in class was a little hard to understand at first, was y equals 1 over x. Now that domain, the domain of this function, its natural domain, does not include 0. So you might say, oh, well, there's a discontinuity at 0. And that's true. But the function is still continuous in general because 0 is not in its domain. And at the points that are in its domain, it's still continuous. So that's what we mean by continuity. We apply the same notions to differentiability. So a function is differentiable at a point if f prime of a equals, delete this equals sign, that should not be there. And then this is the x definition, and this is the h definition. So we have two limit definitions to show whether f prime of a exists, which would stand for the slope of the tangent line to the curve f at the point a. Now, similar to continuity above, a function is differentiable on an interval if it is differentiable at every point of that interval. And it's differentiable in general, as you may have guessed. It's differentiable at every point of its domain. So that's an important recap with those definitions. Next, I want to note this. Since it's often tedious and impractical to imply the limit definition for f prime of a, we use the following shortcuts or rules of differentiation. These are those things some of you in physics may already know, at least a few of them. But we don't use the limit definition every time, especially if we need to get a derivative in an efficient manner. Now, I'm going to be showing you these as shortcuts and just saying that they work, that they're true. I might explain a little bit of the reasoning behind a couple of them. But in a college course on real analysis is what it's called. In real analysis, you do all the proofs behind calculus. You would actually go through each one of these rules and give a proof for why, using the limit definition, for why this rule works. So let's proceed to the rules. All right, so let's look at first the limit of a constant function. So if you have, a function f of x equals c for some real number c, then f prime of x just equals 0. In other words, the derivative of a constant function is 0. Why is that the case? Well, if you picture a constant function, again, if I make a real rough sketch here, it's going to be some horizontal line. This would be the real number c, y equals c. And if you ask, well, what's the slope of this function, or what's the rate of change, or the instantaneous rate of change of this function at any point, well, it's just going to be 0, because any point you pick, the rate of change of that function at that point would be 0. So the slope of a constant is always 0, and the derivative of a constant function is always 0. That's the first rule. Next up, we have the power rule. I typed it up here. Why don't you write that down? What this says is that if you have a power function, a polynomial or of some sort, where it's x to a power n, and I should note here, n is rational. So it could be an integer, it could also be like a half, -1/2. If you have a power, then to take the derivative of that using the shortcut, you just bring this exponent down in front, and then you lower the exponent by 1. A real easy example, the derivative of x to the 4th would lead to, or if I say a function f is equal to x to the 4th, well, then that leads to f prime of x being equal to, I bring this number in front, 4, and then x to the 3rd. And a good way to practice your limit definition is just, you take a derivative with the shortcut, and then can you verify this with the limit definitions? Because in your chapter 3 test, eventually, and on the AP test as well, you're going to have to know the limit definitions in calculus. But can you verify that this is true? Taking derivatives. What's the next rule? So constant multiple rule. I wrote it up here. I like to use a few different notations here. Notice here I'm using f of x and then f prime. Here I'm using y prime. I'm also introducing the ddx operator here. But what this means is if you have a function that consists of a number times the function, well, then when you take the derivative, you can just pull that constant out. You can pull that number out and then do the derivative of the function, and then the overall derivative is just the constant times the derivative of that function. So for example, the one we just saw, let's change it up a little bit. Let's say this was -2 x to the 4th. Well, to calculate f prime using this example, or using this rule, I would just leave the -2 outside and then take the derivative of this portion. I would bring the 4 in front, x, and then lower the exponent by 1. So my overall derivative would be -8 x to the 3rd. And that's one instance of the constant multiple rule. All right, so next we're looking at the sum and difference rule, which I wrote up here. And verbally, I wrote what this means as well. We'll write a sentence for each of these next few rules to help you remember them. But the sum and difference rules basically says if you have a function y equals the sum or difference, plus or minus, meaning either one, of two functions, f of x and g of x, well, then the derivative is just the derivative of the first function and then plus or minus the derivative of the second function. So you can differentiate term by term. That's what we mean by the sum and product rule. Or sorry, the sum and difference rule. Next up is the product rule. These last three are definitely the more challenging ones, and they will take practice to master them. So for the product rule, let me pull this in here. Instead of having a sum or difference of two functions, you have a function, y, that's composed of the product of two functions. So if you have y prime equals, let me just I'll give an example below. If you have y prime equals, maybe like 2x times e to the x, for example. All right, say that's your function, y equals this. Well, this is considered the product of two functions. We have, a polynomial here, a linear function, then we have an exponential function. And when you're differentiating those, the rule is for the derivative, the overall derivative is equal to the first function times the derivative of the second, plus the second function times the derivative of the first. And I like to write that out and say it to myself to help remember it. But here's how I remember it. It's first times the derivative of the second. Format that a little better for you. Plus second times derivative of the first. And say that to yourself a few times. You want to remember that phrasing. First times derivative of second plus second times derivative of first. And it's a little informal here, but in our example, let's see how that would apply. Let's see if we can get a different color. So the overall derivative, oops, no, didn't like that. The overall derivative, I'm just going to use black, y prime would equal the first function, which is 2x, times the derivative of the second function. Ooh, what's the derivative of e to the x? Well, we're going to prove in a subsequent section the derivative of e to the x is e to the x. Yes, that's right. So first times the derivative of the second plus the second function times the derivative of the first. What's the derivative of this function? Well, this is good practice. If y equals 2x, what's the derivative of that? Well, using the power rule, I'll do it like this for a moment. I'm sorry, this is still y. This is just y. So y equals this. I just rewrote it to make it obvious what the power rule would say. And this would be y equals, and then you bring the 1 in front. So it'll be 2 times 1, x to the 0, because you have to lower the exponent by 1. X to the 0 is just 1, so y prime would just be 2. So the derivative of 2x is just 2. We'll practice that more in class. So if our overall derivative, first times derivative of second, plus second times derivative of first. And this would be our derivative. So the product rule can get a little bit more complicated, and you have to use it when there's two functions multiplied, not to be confused with the sum and difference rule, where you just have functions added. So in this one, if I wanted to just give a real quick example. For polynomials like this, if y equals x squared minus 3x, well, to differentiate that, we just go term by term. The derivative of the first term would be 2x. The derivative of the second term would be 3. So the derivative is just 2x minus 3. And those are the sum and difference rule and the product rule. Let's get to our final two rules. All right, so our final two rules are the quotient rule and the chain rule. These are notoriously the most difficult, so you want to spend a little extra time understanding them and practicing them. With the quotient rule, if you have a function y defined as a quotient of two expressions, or two functions, you could call them f of x and g of x, well, then the derivative is equal to this whole big thing. So how can we remember this? What does it mean? Well, the derivative is equal to the bottom function times the derivative of the top minus the top function times the derivative of the bottom all over the bottom squared. And I submit, at least this is the way I first learned it, and I still use it today, the best way to remember that is to memorize the verbal way of saying it. In other words, the quotient rule says bottom times derivative of top minus top times derivative of bottom all over bottom squared. And if you can memorize that phrasing, say it to yourself a few times and kind of always tell it when you need the quotient rule, it's not going to be that hard to carry out. But until you memorize that, it is going to look pretty complex. Just like staring at that formula, it looks confusing. But I'm telling you, once you memorize this saying, we're doing the bottom function times derivative of the top minus top times derivative of bottom all over the bottom function squared. Okay. Let's next go on to the chain rule, our final rule. Oh, I didn't give an example of this. Sorry. Let's do y equals 2x over x minus 1. Let's say you want the derivative of this. Let's follow the rules. Y prime would equal the bottom function, x minus 1, times derivative of the top, which would be 2, minus top function, which is 2x, times the derivative of the bottom. The derivative of x is 1, the 1 in front, and the derivative of a constant is 0. So the derivative of the bottom is 1 times 1 all over the denominator squared. With my Algebra 1 students, I wouldn't really let them say top and bottom because I want them to learn the words numerator and denominator. But with you folks, I know you're very good at that. So I like to say top and bottom. I think it's easier to memorize that. And that would be the general derivative. You could simplify it, and we will practice simplifying, but that's how you use the rule. Okay, finally, the chain rule. This is for composite functions, which you can think of as a function inside of a function. And if you have a function inside of a function, so y is defined as this, f of g of x, then the derivative is going to be f prime of g of x times g prime of x. In other words, the derivative of the function, in terms of g of x, but times this piece I often call the derivative within, or the derivative of the inside function. What's inside? Let's write it out. Verbally, what can we say? The derivative of a composite function is, let's format this a little better. Excuse me. The derivative in terms of the inside function times the derivative of the inside function. Maybe you have a better phrasing of that, but you're doing the derivative of the whole thing times the derivative within. What would this look like? Well, let's say we had a square root function, but inside of that we had a cubic, x cubed minus 2, something like that. So we have a function and an inside function. This will work with logarithms, with exponents. To be inside, and it doesn't have to be underneath, you could have something in the exponent. This would count as a composite function where the inside function is the thing inside the exponent. Or with logs, the inside function, whatever it is, maybe it's a quotient, I don't know. The inside function is the thing inside of the log. So inside doesn't have to be underneath a symbol, but within conceptually. So if that's y, well, let's calculate this. Well, actually, let's rewrite it. So how do you do a derivative like this? And we'll look at a bunch of examples, but you're going to have to start practicing on your own to get these rules down. One way of dealing with radicals is to rewrite them as x cubed minus 2 to the 1/2. Now, if I were to want a different color for this crayon. This is so complicated. Some of my friends call it a crayon. I always said crayon. Oh, just click the color. Duh. Okay. All right. So, consider this thing the inside function. Okay. But first, the first part of the chain rule is we're just going to treat it and take the derivative as if this was like one single entity. Almost as if this whole thing is our g of x. So we're almost just going to act like, okay, this is a blob, and we're going to take the derivative almost as if this was another variable. Okay, this whole expression. And in other words, almost treating it like, let me write it like this, almost like, z to the 1/2. Let's say. Okay, and to take the derivative of that, we do 1/2 in front, z, and then we'd lower it by 1, negative 1/2. So, by that logic, treating this like it's like one entity, the inside function, when we're working in terms of the inside function, y prime would be 1/2. And then in terms of the inside function, it just means keep the inside function the same. That's our entity inside. X cubed minus 2 to the negative 1/2, which follows from what I did up here. But then the second part of the chain rule is if you have a function inside, you always have to multiply by the derivative within, or the derivative of the inside function. Derivative of 2 is a constant, so that's just 0. The derivative of x cubed is 3x squared. And this would be our overall function derivative. So that's the chain rule. I would start practicing these rules on your own. Your homework for the next set is not due until Wednesday, but Tuesday in class, I'm going to expect you coming in knowing how to do these rules, and we're going to employ them in a ton of examples, and we're also going to fine-tune those arguments, how to make those arguments for matching derivatives. All right, thanks for watching this video lecture. I'm Mr. DeRosa, and enjoy your weekend.